So, how is everything? Is it working out?
Yes.
Okay. Okay. I think you might come up with a very different solution. Um, because remember, you know, you can have, you can build a different logical circuit with the same truth table. You know, you can. So, for example, the truth table for exclusive OR is kind of very interesting because you can see that what the truth table going to look like. But there's an infinite number of different, Boolean expression that will provide the same truth table as the exclusive OR. So same thing with the logical circuit. You can build a different logical circuit with the same truth table. Okay. So well, I don't know how can you show this to me, but let me actually whatever your build is, let me actually show the one I can show you the one we have. Let's actually hold on. Okay, now this is one of the example. It's probably the simplest example. You can probably it's gonna be the same as the one you just built, because you have to actually calculate the negation first. So negation B. Oh, sorry. Um, so you build the negation B. So then you have a import A, import B. So the first one you need to go is negation B, right? You build the negation B. And the negation B gonna actually end with A. Okay, so that's basically build the A and negation B. And also the import A gonna be actually used elsewhere. I use a small curve, means that these two wires are not connected. So that basically the way you can actually show. So then the other one is negation A and B directly. Just take this one. So negation A and B. So going through the AND gate. So this is AND gate. AND gate. So this is not. And then these two pass through the OR gate. So this actually build the exclusive OR gate. Okay. So basically I used five gates, 2 NOT gates, 2 AND gates, and 1 OR gate. Okay, so I build the exclusive OR. Do you have the same as I do? Must be similar, right?
Yes, Professor. Same.
Okay,
Yes, same.
that's good. Now, if next thing I want you to do is, if I give you the electric circuit, the logical circuit, now can you actually build the Boolean expression? Okay. So here's the opposite way. Okay. Here's the expression. Now, if you look at this, so first you have 3 inputs, A, B, and a C. Okay. And then, so you're going to pass through each of these gates. So first you need to you need to get to know what does each of the symbol means. Okay. So the one with the round head is AND gate. Okay, this is OR gate. AND. Or, oh, that's AND. Sorry. That's all. Now, what is the logic expression for this one? Can you? Well, I let you think about for like a couple of minutes. That should be that one should be very quick, but you can then we can actually put things together. Okay, what do you get? So here's a and a B, and this is B, this is C. So this is B plus C, right?
Plus B plus C
That's B,
into B into C.
B, and the C. Is that right?
Yes, sir.
So then this and the gate, so that's give you B plus C and the B and C, right?
Into C.
And then, so this is gonna give you the final result gonna be A and the B plus C. Is that right? Okay. Now, this is actually the largest circuit. This is actually the Boolean expression. So they're equivalent. And then the next thing we're going to talk about is, can we simplify this? Now, what's the benefit of simplifying a logical expression? Because we can simplify the logical circuit, right? Now just using imagination, just you imagine this. Now, if two companies, they build the same logic components, same actually electronic circuit, a chip. They build the same chip. Of course, we know that you want to build a chip to perform an operation. Now, two companies can build a chip, but they may have a different logical design, right? Because you know that the two actually chip may actually have the same truth table, but they have completely different logic expression inside built in this chip. Okay, now which chip is better? The one with a simpler design.
Simple.
Why? Because if you use smaller number of gates, smaller number of transistors,
We can
then
incorporate more.
you can consume a less power, right? Also, you're gonna actually it's less complicated, so you can consume less power, and also you will later you will see you will consume actually you're gonna generate less heat, because if you have a more actually transistors working in the circuit, then this is gonna build a lot of heat and consume less power. It's also more reliable because if the design is simple, the reliability is better and also consume less power. So you can actually build two actual electronic circuit based on two different logical actual formula, but you will find out one of the chip is actually definitely better than the other one, because this is actually probably not the issue if the chip is very simple logically. But think about when you have billions of circuits inside, billions of transistors, billions of gates inside. Now, if you have completely different logical design, then you'll probably see the differences here. That's why different company they may basically build the same chip, but the quality is definitely not the same, because some of the chip works extremely well, but the other chip can easily actually heat up, and so that's the problem. And also the reliability is actually not the same. Okay, I think that's pretty much all. So for the module 2, so we still have time, so I can actually start a little bit about the module 3, but I will definitely stop in the middle, and maybe we can talk a little bit about the module 3, and then we can stop. Okay. Okay, let's see. What's the next one we have? Okay, so let's see. Okay, so module 3 is the second part of the Boolean algebra and its application in digital electronics. So we can actually basically focus on the simplification of a logic circuits, because that's so important. And also in module 3, we're going to talk about how can I use this, gates, and use this logic expression to build some kind of, logical device. Okay. And one of the device we call it's called the flip flop. It's called a set reset flip flop. It's a very actually interesting device that can perform very simple job, because you can actually use the flip flop to store 1 bit. Sounds like it's not a big deal, but you can imagine when you actually build a computer memory. So if you can build a computer device that can store 1 bit, then you can build a storage that can store 2 bits, right? And then you can build a storage that can store 8 bits or 1 byte. And then you can build a memory that you can store actually 1 kilobyte and 1 megabyte. You can actually add these things up to build a big device that can store a big data, a whole bunch of data. So that's basically a very good start. That's set reset flip flop is probably the earliest technology we use. But in the modern technology, we may actually store that a bit using different technology. But reset flip flop is a very interesting device that they used in the modern in the digital computer. Okay. Now, so we actually mentioned that there are an infinite number of Boolean expressions that are logically equivalent to one another. So this basically says that there are also an infinite number of corresponding logical circuits that can perform the same functionality, right? Now the question is, how can we tell that a circuit is in the simplest form? Okay. So we can compare two logically equivalent circuits. One requires more digital logical gates than the other does. Now we can make such an assumption, right? So that the one requires more logical gates going to be less reliable, and you're going to consume more power, and also it's going to be actually increase the manufacturing cost. So we can logically assume that the circuit with fewer the circuit with fewer number of components should increase the reliability, decrease the manufacturing cost, and consumes less electrical power. Okay, so eventually this is going to reduce the operational cost. As I mentioned that if we build a very simple logic circuit, one requires 3 gates, the other one requires 5 gates. Okay, now think about we reproduce this and we increase the number of gates proportionally, then one gonna requires 3 million gates, the other one requires 5 million gates. So then you can imagine a very two small circuit. They perform basically the same functionality. One requires 3 million, the other one requires 5 million logical gates. So of course, we prefer the 3 million gates because they're equivalent. They're going to perform the same job, right? So, and also they're easy to manufacture and they are actually consume less power and more reliable. Okay. So the circuit with fewer logic gates will be regarded as the simpler one. Okay. So that's the idea. It's basically, it's not really a definition of which one is simpler, but it's just basically based on our experience. In industry, it's fine. You don't need a definition. You need to actually, you don't have to prove that this is a simpler form. But in practical, we know that the circuit with fewer gates, fewer components, going to be the simpler than the circuits with more components. So that's basically our understanding of this. Okay. So that basically says, how can we simplify a logical circuit? Okay, here's basically the approach. So you can translate the logical circuit into the corresponding Boolean expression. So we did that in the last PowerPoint slide, right? The last slide. Basically, I gave you the logical circuit, and then you can actually just write down the logical expression for this logical circuit. And then we can actually simplify the Boolean expression with algebraic rule says that the reduce the number of turns and all logical operations. So you can reduce the number of and, number of or, number of not. Okay, it's just a similar, it's equivalent to the gates. Okay, and then once you actually simplify this form, and then you can generate a large circuit diagram from the simplified expression with fewer gates or components. So this is basically, you convert the logical circuits into a logical expression, simplify the logical expression, and then rebuild the logical circuits. Okay. So now to this end, there are several rules of Boolean algebra presented in the previous module to reduce the expression to their simplest form. So the Boolean identity, remember the table, like the distributive law, the De Morgan law, and also the commutative law. So you use different laws to in the Boolean identities to these are very useful things to in the simplification of the Boolean expression. Okay, now remember this. Okay, so that was the example we just worked on last time. This is the example we just worked on last time. Okay. Now, let's see. Can we simplify this? Now, if you look at this expression, looks like there's a way you can simplify this, right? Definitely, you can simplify this very easily. Okay. Let's see. So if you look at the second one, now C times B plus C, then what this is equal to?
C and B plus C and C.
Okay.
The distributive law?
Yeah, you can just say C and B plus C and C, right?
Yeah.
And if you don't know the one of the absorption law basically means this is just a C. Now, if you don't know this, then we can simplify as well, because C and B and C and C, then
And
it's
C.
C plus C times B plus C, because
C.
C and the C is C, right?
Yes.
And then you can actually take the C out, so C B plus, oh, I'm sorry, not this one. This is not. I'm actually going back. That's not what I want to do. Actually, this is actually you can take a C out times B, and that's, you can take a 1, right? So because C is C, C and a 1 is C, right? Now B plus 1, B or 1, what is this?
1. 1.
Yeah, this is 1, and this is actually C.
C. Yeah.
But you can directly use absorption rule. So then this is A, B
And B.
plus B times C, right?
C.
Okay.
Yes.
Now can we further simplify this? So A.
And
So in this case, how many operators we have? And, or. So you have a 3 operator, right? You have 3 operator. And but
A
if
and
you
B plus
actually use
C.
commutative law, if you use commutative law, then you can actually simplify this.
A and B plus C.
A plus, so you eventually can get A plus C and B, right?
Yeah. Yes.
Because you can switch B and C, and then you can take a B out.
Mm.
So in that case, you only need 2 gates, right? That's OR, that's AND, right?
Mm.
Instead of 2 AND, 1 OR. So in that case, you can say from actually, Boolean logical, you don't see much difference, but this is actually definitely reduce the number of gates. In this case, there's only 1 gate and one OR gate, 1 AND gate, right? And this one, you need 2 AND gate, 1 OR gate. So let's draw this first. This one and this one, they are identical. They are basically the same identical logic expression. But if you draw the circuit, you will see the difference, because one only requires 2 gates, the other one requires 3 gates, right? Okay, let's take a look. So now, this is the one we have. Yeah, this is the one we have. We know that. Okay, so now let's see. We can actually do the simplification. Okay, so this is the one way of doing this. So I'm not going to actually go over this again, but eventually we get this one, right? So now here, I just actually doing this very carefully. So for each operation, I actually provide the name why I can do this based on the, Boolean identities. Okay, so this is the reasoning, this is a kind of a reasoning, but for some of these, you can easily see, because from here to here, from here to here, you can easily see that's, that's, oh no, I'm sorry, not here. From here to here, you can easily A and the B and is the same as B and A. But in here, I just add additional one. I use the commutative law, x, y, and so basically, if you actually you do the job very carefully, you have to actually, for each operation, you have to tell the reason why you can do this. So that's why I just provide all these reasons. Okay, here. Now, also, I listed all the number of gates here. Okay. So every time when I reduce, now here 1, 2, 3, 4, 5, and then when I times out, 1, 2, 3, 4, 5, 6, 7, I use actually 7 gates, and then this basically tells us how can I reduce the number of gates, and eventually the number of gates becomes 2. In the previous one, you still need 3 gates. Okay. Okay. So then, to build the circuit, so then you need to build the circuit. First, you need to build the OR gate, A and C. So A and C. Okay. And then A and C and a B. So that's B and C. Now you can see that I can use that. But if I build the gates from here, what the logical circuit gonna look like? If I say A and B plus B and C, if I build a circuit based on this logic expression, so I can have A, B, and a C. So I'm gonna say A, B, I use the AND gate, right? And the B and the C, I use another AND gate, and then I build, right? So now this logical circuit gonna perform exactly the same as this. But one requires 2 gates, the other one requires 3 gates. Now you can tell which one is simpler, right? Of course, this one is simpler. That's the simplest of all. Okay. So basically, when I say this is that when you say, how can I define simplification? Which one is simpler? Mathematically, it's not easy, but practically you can always tell which one is simpler, because the one that requires fewer components, requires fewer gates, gonna be the simpler one. Okay. So this way I actually simplify the logic circuit. Okay. So again, I just listed the advantage of these simpler gates: decrease the manufacturing cost, increase the operating speed. Because if the electronic, the speed of electricity is very fast. It's close to the speed of light. But however, it still has some speed. Now, if the electricity is going to pass too many components, it's going to slow the things down. So if you have a fewer gates, then it can increase the operating speed. Okay, there's a less delay. The delay is very small. You cannot tell much. But think about if you have the delay like a microsecond or millisecond delay, and if the millisecond delay multiplied by 1 million, that delay going to be significant, right? So if you can decrease the delay, you're going to less delay time for the input signal transition to the output signal. So there's always delay. That's the reason why when you use the memory, if the memory is actually has, it's a more actually, if you actually using the modern actually memory chip, like you have a like you in modern times the memory is very big. You can have a 16 gigabit memory, even 32 gigabit memory. The memory actually capacity is much higher, but you will realize the delay is actually also higher. Okay, delay is also higher. But with the technology, so somehow the delay per unit is smaller, but because you have so many different components inside this, so overall there's still some kind of delay. So that's a problem. So that's why building a simpler logical circuit is very important in modern computers design. So if you can actually simplify the circuit, a little bit, it could actually reduce the overall delay. Okay. Also reduce the power consumption, improve the reliability. Okay, so that's for sure. Because for each component, there's always some kind of glitch in there. So if you have more components, if there's something wrong with one small actually gate, then it's gonna cause problem. So the fewer the components, the more reliable it's gonna be. Okay. Okay. Another one. Let's actually do this. That's the last one we're gonna actually work on. So I'm gonna stop after this. Now you can see it's funny. I just erased that one. This is actually interesting. Try to avoid this, right? Because if you have an import A, and you're gonna say, okay, I just actually put another one and I'll put. This doesn't make any sense because that's if it's A, then you can have an A and also A and A. It is A, right? Based on these, the large Boolean identity, it is an A. Now, so why just to say eliminate this directly, just to put A? Why you want to put another gate? That's a waste of money and a waste of time. So that's kind of stupid design. That's an example of a stupid design. But let's say how can we actually simplify this the circuit. Okay. Let's actually now what are you going to do in this case? The first thing you're going to do is convert this into a logical expression, right? Convert the logical circuit into logic expression. Okay. And then you can simplify the logical expression, and once you simplify logical expression, try to reduce the number of operations, because each operation is corresponding to a gate. And then draw the things again. Okay. Okay, so let's see. I think I'm gonna stop right here, and I'm still gonna be around. If you want to actually, if you after your simplification, you can just discuss with me the answer. But otherwise, if you want to leave, you can leave right now. I will actually give you the answer in the next class. So I'm not going to work on this, but I let you work on this. So I will give you the provide my answers for this. Now, if your answer is different, don't just say, oh, I'm wrong. Probably not, because remember that you may actually have different logical design, but the truth table going to be the same. So it's not, if it's different, that's probably okay. But the only thing is that try as much as you can to reduce the number of gates. Okay, reduce the number of components. Okay, I think I'm gonna stop right here, and so we're gonna continue our discussion on next Wednesday. So okay, that's pretty much all for today. So if you have any questions. Okay, let me actually stop the recording.